Thank you, Ross. So I would like to discuss some research where we've been looking at the potential for aftershocks in the far field. So we're looking at regions well beyond the traditional aftershock zone. And we're only focusing on the larger events, magnitude 5.5 and greater. So the main motivation for this research is the aftershock sequence, the global aftershock sequence that Fred Pollitz and others have observed following the 2012 magnitude 8.6 event. So what I'm showing here on the left is the magnitude 8.6, and then the 24 hours following that, you have this large increase in seismicity at distances well beyond the static stress region here. So what Pollitz and others are showing here on the right is the significance of this rate increase in the far field. And what you see is immediately is this multi-day increase in far field activity, and they've extended this to look at some of the 5 greatest subduction events, and you see a less pronounced, but you still see an increase following the Mainshocks. So what we're interested in looking at in this study is the significance of a potential hazard in the far field due to the transient stresses from the great earthquakes. So the main question we want to answer is whether this is an anomalous single occurrence of post-shocks following the magnitude 8.6 event in 2012. And what we use is we perform a catalog study looking only at the largest events, and we define an elevated strain region for each event, and that way we can evaluate rate curves and look for changes in the activity and possibly try to assess if we can determine what makes the magnitude 6 event unique. So what we use is 35 years worth of catalog data. So we use the Global Centroid Moment Tensor Catalog, and what I'm showing in this figure is the distribution of large main shocks. So the colored symbols represent the magnitude 7.5s and greater. So we treat each main shock as a source for a transient stress in the far field. And what we focus on is the region of elevated strain due to this particular main shock. And that way we can systematically examine all magnitude 5.5 and greater events to develop the rate curves so we can look for changes during the time periods after this transient stress. So to define the region of elevated strain, we use some empirical scaling relationships. And what I'm showing in this figure is 2 examples for a magnitude 7.6 and a magnitude 7.9. And we start by declustering the catalog because we want to remove all near field activity, because we're only interested in the rate change in the far field activity. As we've just heard, we know that there's going to be an increase in near field aftershock zones, but we're only interested in the far field activity. So we use an exclusion zone method to remove all near field activity when we use a 2.5 estimated fault length using these relationships from Wells and Coppersmith. And what I'm showing here is that would be like the white region here. And then we select all seismicity within the shaded region, which is defined by a 0.1 microstrain limit, which is approximately 3 kilopascals. And that's estimated using a peak strain as a function of the magnitude. So additionally, we model the strain field, and that way we have a secondary result to look at the empirical scaling with this modeled scaling. So what I'm showing here is the modeled strain field for a magnitude 7.9 strike slip event. And what I'm showing here on the left is the 0.1 microstrain and greater region that is due to the long period surface waves from the main shock. So we estimate the strain magnitude from that, and then this becomes our region where we then select the seismicity to develop the rate curves and to look at the changes in activity. On the right, I'm showing the significance of the spatial scaling. So the blue circle in the inner, or the blue dashed line, so that's showing a 0.2 microstrain. We use a 0.1 microstrain, which is the green, and we've also tested the 0.05 microstrain out to the red. So I just wanted to show the significance of the scaling and what a significant strain range would be for these different scales.
Where's the exclusion zone in that picture?
So the exclusion zone in this picture is not, it's in this picture, so that's the white circle there. It's not shown in this one. So this would extend 2.5 fault lengths there. So for a 7.9, that would be approximately 250 kilometers or so. So to develop the rate curves, we use what I'm showing here in this schematic. So time 0 would be relative to each main shock. And then we are taking all magnitude 5.5 and greater events within that high strain region. And we then develop a rate curve that is smoothed using a 3-day half-width for plus or minus 1 year. We develop confidence intervals from that using a Monte Carlo scheme that perturbs the catalog, and we simulate this 200 times, and that way we can get an estimate for the range of activity. And what I'm showing here does not represent a global background rate, because we are using a spatial scaling so that all of the events that we're looking at are only in this high strain region. So what this is representing is a deviation from the background rate, not necessarily a global background rate. So with these rate curves, we're then able to stack the different main shocks that we're interested in looking at and look for significant changes in activity. So what I'm showing here are 3 different stacks of main shocks. So on the right, on the top, we have all of the magnitude 7.5s and graders, and in the middle we have all the magnitude 8s, and in the bottom we have the 8.5s. And immediately what pops out is you don't see any systematic increase immediately following this transient stress. So this is different from what Pollitz and others were showing following the 2012 event, because we're not seeing that when we systematically look at all of the events in the catalog. So we further explore this data set, and we want to look at the spatial temporal relationship between the timing of the post shocks and the main shocks. So what I'm showing here is all of the stacked seismicity in the far field for plus or minus 1 day. And interestingly, we don't see any immediate triggering of any large events. And this is consistent with previous work, but it's inconsistent with the ubiquitous nature of triggered microseismicity that's often reported following large amplitude surface waves. And in this, using our spatial scaling relationship, the first event that we see occurring is 8.5 hours after the main shocks in the far field. So to further explore this, we also separate by mechanism. So what I'm showing here are the rate curves using only the strike slip events, reverse events, and normal and oblique events separated out. And in this, you can see that you do see a rate increase in the strike slip and normal rate curves, but we're not seeing this in the oblique or reverse events. So we wanted to explore where this increase is coming from, because the strike slip event is consistent with what we see in Pollitz and others' work, and we also see this in the normal rate curves. So we perform this same exercise by raising the magnitude, and we look only at the magnitude 8 and greater, and we still see this increase for the strike slip events here, and we also see this for the normal events. We're not seeing an increase above the confidence intervals immediately following the reverse events or the oblique events. But we wanted to know where these increases were coming from in the normal and strike slip events. So by looking at the individual rate curves for each one, we were able to determine that each increase in activity is due to a single event. So what I'm showing here is the normal event in 1977, which is a magnitude 8.3, which is the result for the increase that we observed in our rate curves. And on the top left is the synthetic strain field that we calculate, and the yellow triangles show the seismicity along the plate boundary that you see occurring within the first 20 days following the main shock. And you can see in this rate curve for this event here that 2 days afterwards, we start to see an increase that persists and is above the background, or is beyond the confidence intervals 10 days following, and persists for 20 days. On the bottom left, I'm showing the duration that we were above the strain threshold. So each one of these events was at an elevated strain for tens of seconds. For the strike slip event, the increase is due to the magnitude 8.6, which Pollitz and others have pointed out previously. So what I'm showing here is the same figures where we're looking at the peak strain and the seismicity in the 20 days following. You can see that this is a much more energetic event. It is a higher magnitude, and the strain field is much greater. Additionally, you see that the activity is occurring in the region that experienced an elevated strain for more than 100 seconds, and that's shown here in the bottom figure. And you can see that this, using just the magnitude 8.6, that there is a rate increase immediately following, with the first event occurring 10 hours afterwards and persists for 2 days. So to investigate whether we see anything else, we remove these events from our study, and we recalculate everything, and you can see with the strike slip event, you do have this increase immediately afterwards, and we remove it, that it's no longer there. And we've done this for multiple simulations using multiple different combinations of events, and we don't see the increase when we take out the 2 events that have been shown to cause this. So, to summarize, we utilize 35 years of global catalog data. We focus only on the magnitude 5.5 and greater events. We don't see any immediate triggering, and we conclude that the global increase following the magnitude 8.6 in 2012 is a unique occurrence, and we're not finding any evidence for a significant increase of hazard at distances greater than 2.5 fault lengths following these great main shocks. Thank you.
It was a fascinating presentation. Questions? Is it possible that in that kind of 8-hour blind spot that you're missing the real signal in this problem?
For the larger events, I would say that the catalog is complete. We're not going to be missing the magnitude 5.5 and greater. What I would think is occurring if these are potentially triggered events, is some type of cascading of microseismicity to that during that blind spot, which leads to why is there a delayed phenomena for these larger events, because we don't see any immediate triggering.
So have you tried just taking those 8 hours after every one of those events, stacking those, and seeing how the global earthquake rates compare to typical earthquake rates to make sure what you said is true?
We have not done that. What we have done is just looked at the entire day afterwards, and then we've also reduced the exclusion zone. And once we move beyond or lower than approximately 2 fault lengths, you do see this large increase, but then you would expect to see that because of the static offsets and the stress changes associated.
Right. Okay. All right. Thank you very much.